morning students, welcome back in this lecture of the vector integration. Today I am going to discuss the Stokes theorem and then we will solve question based on Stokes theorem, and with the help of a problem I will verify my Stokes theorem. So let us have the proof of the Stokes theorem. Your statement is, let S is an open surface bounded by a closed curve C, and suppose that this is your vector point function with a vector point function having partial derivatives first order partial derivatives then your line integral f dot dr is equal to your surface integral curl f dot and ds. Then your line integral is same as your surface integral, where your n cap is the outward normal to the surface S. Where n cap is the outward normal to this surface S. So sometimes it becomes very difficult to find out the surface integral. In that case, we can have the value of this surface integral with the help of the line integral. Now let us verify this theorem. So proof: let n cap is the normal to this surface S which have angles alpha, beta, gamma from the coordinate axis. Let n is the outer normal having angles alpha, beta, gamma to the coordinate axis. Then your n cap will be cos alpha I plus cos beta j plus cos gamma k. Now it is given that also your f is equal to f1i plus f2j plus f3k. R is your radial vector. Your R is xi plus yj plus zk. Your curl of f will be I j k del by del x del by del y del upon del z f1 f2 f3. So it is equal to I time, now this will be your del f3 upon del y minus del f2 upon del z. Then we will have plus j del f1 upon del z minus del f3 upon del x. Then we will have plus k del f2 upon del x minus del f1 upon del y. Okay, so this is your curl of f. Now let us write this equation in Cartesian form. So therefore your integral C f dot dr equal to curl f dot n ds will give, now this line integral will be f dot dr. Now your dr will be dxi plus dyj plus dzk. So this left hand side will become, this left hand side will be your f1 dx plus f2 dy plus f3 dz. So this is your left hand side, and in the right hand side we will have the surface integral. Now your curl f dot n, your n is cos alpha I plus cos beta j plus cos gamma k, cos gamma k. So your curl f dot n will give you del f3 upon del y minus del f2 upon del z into cos alpha. Then we will have del f1 upon del z minus del f3 upon del x cos beta. Then your third term will be del f2 upon del y, del f2 upon del x minus del f1 upon del y, and then cos gamma, and at outside we will have ds. So this is your Stokes theorem in Cartesian form, which is the Stokes theorem in Cartesian form. Now we will prove this part. Now for that we will take the left hand side and we will show that this left hand side is equal to this right hand side. Okay, so we will start with the line integral c f1 dx. Now let us assume z equal to z equal to f of xy is the equation of the surface and is the equation of the open surface S, which is bounded by your closed curve C. So let us draw this surface. Say this is your x-axis, say this is your y-axis, say this is your z-axis, and say it is x-axis. And this is your open surface, which is bounded by a closed curve C. And let us take its projection in the xy plane. And say this is your R. Now let us draw an elementary area. This one. So this is your projection of this surface in the xy plane, and say this is your R, and now this will be parallel to, this is your parallel to your y-axis, so this will be your dy and this is your dx. So this area will be your dx into dy. Okay, and say this is your y, and suppose that let z equal to phi xy is the equation of surface S, which is bounded by a closed curve C, and let us assume its projection in xy plane is R, and let us assume its projection in the xy plane is R, then our dx into dy will be equal to cos gamma into ds. So in this case your dx into dy will be cos gamma into ds. Now let us take the left hand side and we will evaluate the integral c f1 dx. Now integral c f1, your f1 is a function of x, y, z into dx. So we can write it as c. Now your z is some another function of x, y, z, some another function of x, y, so we can write it as phi, and then we have dx. We can also write it as f1 x, y, phi into dx plus 0 into dy. Now we have this line integral, and now with the help of the Green's theorem for plane, this line integral can be written in terms of surface integral in a plane. So using the Green's theorem, so by Green's theorem, your Green's theorem is because by Green's theorem for plane we have integral m dx plus n dy equal to the surface integral for the plane del n upon del x minus del m upon del y into dx dy into dx dy. So this is your Green's theorem. Now with the help of this Green's theorem, this will be your, say this is your m, this is your n. So the first term will be your del n upon del x, that is your 0, and minus del m upon del y. So we have therefore your line integral c f1 x, y, z dx is equal to, now this will become your surface integral over the plane R. Now this will be minus del m upon, say, del f1 x, y, phi upon del y, and then the differentiation with respect to x and y. So this is by Green's theorem. Now your f is a function of x, y, and z. Phi is your z. So with the help of the definition of the partial derivative, with the help of the chain rule, we can write it as, so this can be written as del f1 upon del x. Now first differentiate with respect to x. So this will be your del f1 upon del x into del x upon del y. As your x and y are independent, so that term will be 0. Then we will have del f1 upon del y and del y upon del y, that is 0. Then we will have del f1 upon del phi. Phi and z are same because your phi is same as z. So we can write it as del phi upon del z into del z upon del x into del z upon del y or del phi upon del y. So I am writing here del phi upon del y. Then we have dx dy. So we have this value for the plane R. Now we know that the direction cosine of z equal to phi xy R, the direction cosine of this surface R del phi upon del x, del phi upon del y, and minus 1. These are the direction cosine of this surface. Again, initially we have assumed that n cap equal to cos alpha I plus cos beta j plus cos gamma k. So that means cos alpha, cos beta, cos gamma are also the direction cosine of the surface. So these are the direction cosine of the normal to this surface. Again, we know that the direction cosine of normal to this surface are this one. And again we have the direction cosine of n cap as cos alpha, cos beta, cos gamma. So that means these two will coincide with each other. So hence we have cos alpha upon the first term del phi upon del x equal to cos beta upon del phi upon del y, and then we have cos gamma upon minus 1. So from here you can see that your del phi upon del y is equal to minus cos beta upon cos gamma. So this is your del phi upon del y. Now we have the value of del phi upon del y, and now let us put this value in this equation number 2. So by 2 we have the line integral C f1 xyz into dx equal to minus double integral r. Your first term is del f1 upon del y. Now the value of del phi upon del y is equal to minus cos beta upon cos gamma. So this will be your minus del f1 upon del z into cos beta upon cos gamma, and then dx into dy. Okay. Now your projection, we have the projection of ds as dx into dy, which is your, we have the projection of ds as r, and which is, with the help of this equation we have the value of dx into dy as cos gamma into ds. So we can also write it as the surface integral, just put the value of dx dy and multiply this cos gamma. So we have cos gamma del f1 upon del y, then here we will have minus del f1 upon del z cos beta, and now your dx into dy will be cos gamma. So that cos gamma will get cancelled, so we have into ds. So this is equal to, so it is equal to, therefore the first line integral c1 f1 xyz dx is equal to the surface integral del f1 upon del z cos beta minus del f1 upon del y cos gamma into ds. So we have evaluated one line integral. Similarly, we can evaluate remaining two line integral, and if you add these three line integral, then we can say that these three line integral will give you the right hand side of the that Stokes theorem, in which was written in the Cartesian form. So similarly, when you take f2 here, when you take f2 dy, then we will differentiate. Then again, with the help of your Gauss theorem, we can have the value of this term, that will be your del f2 upon del xy. So similarly, your integral c f2 xyz dy will be equal to, so I am not going in the proof, I am writing it directly. So this will be equal to as del f2 upon del x cos gamma minus del f2 upon del z cos alpha into ds, and your third integral will be equal to the double integral del f3 upon del y cos alpha minus del f3 upon del z cos beta into ds. Okay, we have these two line integral. First one is del f1 upon del z into cos beta minus del f1 upon del y cos gamma into ds. Now if you add these three line integrals, then you will get the right hand side of the Stokes theorem, which was written in the Cartesian form. So on adding, say this is equation number 3, 4, 5. On addition of 3 plus 4, 3, 4 and 5, we get the result. So as you add these three equations, our left hand side, which is your line integral, will be equal to the surface integral in Cartesian form. So this is the proof of your Stokes theorem. Now let us solve few few questions based on this Stokes theorem. That means with the help of this Stokes theorem, we will try to evaluate the surface integral or the line integral, and then we will verify our Stokes theorem. We will verify our Stokes theorem for a given surface. So our first question is to evaluate the line integral by Stokes theorem where your f is equal to y square I plus x square j minus x plus zk, and C is the boundary of the triangle with vertices 0, 0, 0, 1, 0, 0 and 0, 1, 0. So evaluate this line integral by Stokes theorem where your curve C is the boundary of the triangle with vertices 0, 0, 0, 1, 0, 0 and 0, 1, 0. So solution, say this is your x-axis, say this is your y-axis, and say this is your z-axis. Here you can say that your origin is this point O, then we have x as 1, so this will be 1, 0, 0. Then we have y as 0, x as 0, y as 1, so this will be somewhere this point 0, 1, 0. So we have the triangle with vertices these three. So say this is your O, say this is your A, this is your B. Now you can say that it's the equation of this line will be equal to y equal to mx, and where your gradient is equal to 1. So this will be your line y equal to x. For this line we have x equal to 1, so this is your x equal to 1, and for this line we have y equal to 0. Now if you want to evaluate this line integral directly, then take this line OA, then we will take the line integral along AB, then we will take the line integral along BO. But here we have to evaluate this line integral with the help of the Stokes theorem. So that means we will use the surface integral. So solution, let us find out by Stokes theorem your line integral C f dot dr will be equal to the double integral curl f dot n into ds. Here your normal vector will be your unit normal to this surface xy, to this curve, to this triangle will be your k. The normal to this surface, this plane is equal to the orthonormal to the z-axis. So your n cap is k cap. So let us find out curl f. Your curl f will be equal to I j k del by del x, del by del y, del by del z. Then we have the components as y square, x square and minus x plus z. Now this is equal to, now the differentiation of this will be 0, again this is your 0, and with respect to j, this will be your, so we have minus j, your coefficient of I is 0, then we have minus j, differentiation with respect to x will be 1, and then the differentiation of this will be your 0, and then with respect to k, your differentiation of x square will be your 2x, and then your differentiation with respect to y square will be 2y, and your differentiation with respect to, for j we will have this one as minus 1 and this will be 0. So this is equal to minus minus plus, so this is your j into 2k times x minus y. So therefore our line integral C f dot dr is equal to surface integral curl f. So we have curl f dot n is equal to a cat. So this will be 2 times x minus y into ds, and this is equal to 2 times x minus y. This will be just dx into dy upon n dot k. Your n is k, so that will be your 1. And here you can see that if you take the vertical strip, now here you can see that your x will start from 0 to 1. So we have x equal to 0 to 1, and your y will start from 0 to x. So let us evaluate this surface integral, and this is equal to 2 times x is from 0 to 1. Let us differentiate with respect to y. So this will be your x into y minus y square upon 2, and then we will have the limits from 0 to x, and then the integration with respect to x. So this is equal to x equal to 0 to 1. So we have x square minus x square upon 2 into dx. So you can say that this is your 2x square minus x square. So this is your x square upon 2. So this 2 will get cancelled, and integration of x square will be x cube upon 3. And if you put the limit, then we will have 1 by 3. So the value of this line integral is equal to 1 by 3. And you can also evaluate this line integral with the help of these 3 lines. Now, let us verify the Stokes theorem with the help of few questions. So our first question is to verify Stokes theorem for f equal to x square plus y square I minus 2xyj taken round the rectangle bounded by the lines x equal to plus minus a, y equal to 0, y equal to b. So here we will have to evaluate the surface integral as well as the line integral. This is your question number 1, and then a similar question is to verify Stokes theorem for f equal to x square I plus xyj, where taken round the square x equal to 0, y equal to 0, x equal to a, y equal to a in the plane z equal to 0. These two questions are similar to each other. Here we have the rectangle and here we have the square. Nothing else. So I am going to verify the first question. So I am going to solve the first question, solution of the first part. Let us evaluate the line integral as well as the surface integral. Here we have to show that your line integral C f dot dr is equal to your surface integral curl f dot n ds. First of all, let us evaluate this surface integral because it is easy to evaluate this one. For the line integral, we will have to take the 4 integrals. So first of all, let us evaluate the surface integral. Now here you have the lines as x equal to plus a, so this will be your x equal to plus a line. Then we have x equal to minus a. Then we have the line y equal to 0, and then we have the line y equal to b. So this is your x-axis, say this is your y axis and this is your z axis. Again your normal vector will be k cat, and this will be your point a comma 0, this will be your a comma b, here we will have the minus a comma b, this will be your minus a comma b. So for the surface integral we will take a vertical strip, say this one, and you can see that the value of y is from 0 to b and your value of x is from minus a to a. Your unit normal vector will be your k cat, and let us evaluate the curl of f. Your curl of f will be equal to ijk del by del x, del by del y, del by del z. Then we have x square plus y square. Then we have minus 2xy, and third component will be 0. Now this is the component of y will be 0, and for the component of j will be your, this will be 0, again this will be 0, and this will be just k time, this will be your minus 2y, and again this will be your minus 2y. So this will be your minus 4y into k cat. So your curl f is this one. Therefore your surface integral will be equal to, your curl f is minus 4 y into k cat, then we have k cat into dx into dy for the plane, this one. For this plane, if you take the projection, that will be your dx into dy upon n dot k, and your n is k cat, so that will be 1, and this is equal to r. Now this k dot k is 1, so we have minus 4, let us take this minus 4 outside, and in the bracket we will have y into dx into dy. Now just guess the limits. The value of y will be from 0 to b, and the value of x will be from minus a to plus a. Now integration of y will be y square by 2, so this will give you minus 2b square, and then we have x from minus a to a dx. So this will give you 2a, so this is equal to minus 4ab square. So that means the value of this surface integral is equal to minus 4ab square. Now we will show that this line integral is also equal to minus 4ab square. Now your line integral is a sum of 4 line integrals, one along, say this is your a, say this is your b, say this one is b, c, and this one is d. So your line integral will be the sum of 4 line integrals plus your bc, then we will have cd, then we will have dA. So this one is equation number 2, and say this is your 1. Now we will evaluate all these line integrals one by one. Now for the first line integral, for the first line integral AB, f dot dr, for this line integral, you can see that our y is 0. Now if you put y equal to 0 here, then you can see that your f is just x square into I. So your f is x square into I, and your dr will be dxi plus dyj plus dzk. So this will be your x square into dx. So this is equal to x square into dx, and the values of x will be from minus a to plus a for this line AB. And as the function is given, so we can write it 2 times, and the integration of x square will be x cube upon 3. So this will be a 2.3 a cube. So the value of the first line integral is 2.3 a cube. Then the second line integral. Now for this line integral BC, your x is a, so your dx will be 0. So as your dx will be 0, so your dr will be j times dy. So this term will be 0. J times dy will give you minus 2x into y into dy. As your x is a, so this will be your, this line integral will be your minus your x is a, so your dx will be 0, so your dr will be dy into j, so this will be a minus 2xy into dy, minus 2x is your a, y into dy, and the value of y will be from 0 to b, and we have the limit of y from 0 to b, and the integration of y will be y square by 2, so this will be minus ab square, and then your third line CD. This third line integral will be, now for this third line integral we have y equal to b, so your dy will be 0. As our dy is 0, so this will be your x square plus y square, y is b into dx. And again for this third line we have the value of x from a to minus a. Now this will be equal to, now the integration of x square will be x cube upon 3. So we can write it as x cube upon 3 plus b square into x, and the limits from a to minus a. So this will be equal to minus a cube upon 3, and again this will be your a cube upon 3, so this is your minus 2 a cube upon 3, and here we will have, for the upper limit it is minus a, and again for the lower limit it will be your minus a, so this will be your minus 2a b square. So this is the value of third line integral. Now the fourth line integral, now your fourth line integral will be the line integral along dA. And for this line we have x equal to minus a, so your dx will be 0, and therefore we have this one equal to minus 2x into y into dy. Your x is minus a, so this will be your 2a into y into dy, and the limits of y will be from b to 0. Your y will move from b to 0. Now the integration of y will be y square by 2, so this will be your a minus a b square. So this value is minus a b square. Now let us add all these four line integrals. So by 2, your line integral c f dot dr will be equal to, now let us put these all four line integrals in the equation number 2. So here you can see that this is your first integral, and your 2 upon 3 a cube will cancel with this one. This is your minus ab square, this is your minus 2ab square, so this means we have minus 3ab square, and this is your minus ab square. So this is equal to minus 4ab square. So you can see that from equation number 1 and 3, hence by 1 and 3 we can say that our line integral is same as the surface integral. So our Stokes theorem is verified. Then we have the last question of this Stokes theorem. Similarly, you can prove this second part. Now we have to verify the Stokes theorem for f equal to 2x minus y I minus y z square j minus y square z k, where your S is the upper half of the sphere x square plus y square plus z square equal to 1, with bounded by its projection on the xy plane, bounded by its projection on the xy plane. So solution, say this is your x-axis, so this is your y-axis, and say this is your z-axis. Now here we have a surface, so this is your surface which is bounded by a circle which is bounded by its projection in the xy plane. So this is your projection of this sphere in xy plane. Now you can see that this surface S is bounded by its projection in the xy plane, which is your circle x square plus y square equal to 1. And at here we will have x as minus 1, your y will be your minus 1, and here we will have y at plus 1. This is your plane z equal to 0. So we have to verify this Stokes theorem for the upper half of the sphere, which is bounded by the projection of this sphere in the xy plane. Okay. Now for that we have to show that this line integral is same as the surface integral. Now let us evaluate the line integral first. Your line integral will be equal to, your f is this one. So f dot dr means dr is dxi plus dyj plus dzk. So this will be equal to 2x minus y into dx minus yz square into dy minus y square into z into dz. Now for the line integral we have at z equal to 0, so we have dz equal to 0. Now here we will have a circle, and the parametric coordinates of this circle will be x equal to cos t and y equal to sin t. So therefore your line integral c f dot dr will be equal to, now put your z equal to 0, so this term will get cancelled, again this is your 0. So we have 2x, that means 2 cos t minus y sin t into dx, and this dx can be written as dx upon dt into dt. Now the whole right hand side in terms of t, and your t for this complete circle, for this circle your t will vary from 0 to 2 pi. So here we have 0 to 2 pi, then 2 cos t minus sin t, and here your dx by dt will be minus sin t into dt. So this is equal to 0 to 2 pi minus 2 cos t sin t. This will be a minus minus plus, so sin square t into dt. Now 2 sin theta cos theta is sin 2 theta. So the first line integral will be equal to, this is your sin 2t. Now with the help of cos 2t, your cos 2t is 1 minus 2 sin square t. So your sin square t will be 1 minus cos 2t upon 2. Now your integration will be equal to, now the integration of sin 2t will be minus minus plus cos 2t upon 2. Integration of 1 will be 3 by 2. Integration of cos 2t will be again 1 by 4 sin 2t. Now if you put the limits from 0 to 2 pi, you can see that your cos 4 pi is same as cos 0. The first term is 0. Again for the third term, your sin 2 pi is 0 and your sin 0 is 0. So this is equal to 2 pi upon 2. So this is equal to pi. So the value of this line integral is pi. Now let us evaluate the surface integral. Now for the surface integral, let us find out the curl of f. So your curl f will be I, j, k, del by del x, del by del y, del by del z, Then we have the components of f as 2x minus y z square minus z square y minus y square z. So this is equal to, now the first term will be your 2yz, this will be again 2yz, so this will be your 0. For j, again we have 0, so again for k, this will give you 0 and this will be your plus 1. So this curl f is k cap. Therefore, your surface integral is equal to, the surface integral, your curl f is k cap and your unit normal to this surface will be your k cap. Now if you take the projection of ds will be dx into dy upon n dot k, and your n is k, so this will be your k dot k, and here we will have r. So this is 1, again this is 1, so we will simply have dx into dy. Then this is your simply dx into dy and the over the plane r. Now the area of this circle will be equal to pi r square. This is your area and the area of the circle will be pi r square. So this is your pi. Therefore, we can say that our line integral is same as our surface integral. Hence, our Stokes theorem is verified. This is all about this Stokes theorem. Now, in my next lecture, I will discuss the Green's theorem for the plane and we will give the proof of Green's theorem. Then finally, I will solve question based on Green's theorem, and that will complete our this engineering mathematics 1. Thank you so much for joining this lecture.